Let's talk about Riemann sums. Now remember, we're trying to approximate the area under the curve between A and B. And what we want to do is we want to use the sum of the areas of rectangles to do that, okay? So in order to do this, we first want to define something called a partition. Now, let me pause for a moment and produce a number line to help you understand the idea of a partition. Okay, voila. So now you see this number line has magically appeared on your screen. Okay, and I wanted to find a partition of a closed interval AB. So what I did was I created my interval AB right here. I labeled the left endpoint A. I labeled the right endpoint B. What I want to do now is I want to label all of these points in between. So we're going to call the very first point x naught or x sub 0. And the very last point is going to be x sub n. And then we're just going to enumerate as we go along. So that the second point would be x1 and then x2 and so on and so forth. So with a partition, what we're trying to do is we're trying to break up this interval AB into n subintervals. So a partition of an interval is really a collection of subintervals. And these subintervals will be like x0, x1, x1, x2, so on and so forth. If I wanted to talk about a generic subinterval, I would put xi minus 1, xi, and then, the last one would be xn minus 1 and xn. So this xi minus 1 xi subinterval, that's just supposed to represent a general subinterval. General subinterval. Okay, so I hope it's clear what I mean by a subinterval. A subinterval is an interval within your interval. So maybe I should label that as well. This is an interval within the interval AB. Okay, so that's what a partition is. I'm going to highlight that. And now let's look at a special case of a partition. Let's look at something we call a regular partition. So let me push this page up a little bit. If we create a regular partition of this interval AB with n, now here's the important thing, they're equally spaced. So a general partition does not have to be equally spaced, but a regular partition means that it's equally spaced, all right? So we got n equally spaced subintervals. The width of this subinterval is going to be delta x. And we have a formula for what delta x is going to be. It's going to be the length of the entire interval, which is b minus a, and then we're going to divide it by the number of subintervals, which is n. So this is going to give us the width of a regular partition. Okay. Now the ith subinterval, or some generic non-specified subinterval, is denoted xi minus 1 xi. So we had mentioned that earlier up above. All right. The left endpoint of the ith subinterval is xi minus 1, and the right endpoint of the ith subinterval is xi. Now, the way that we're going to approximate the area is with area of a rectangle. And as we know, the area of a rectangle is going to be given by the height times the width. Okay, so I want us to look at this, this rule we have here, this left endpoint approximation rule. So I've drawn a picture on the right side, or I didn't draw it, but we have this curve here. This curve here is y equal to f of x, okay? And I hope you can see that we have a bunch of rectangles. And these rectangles, they're not going to capture the exact area under the curve from A to B. This only is an approximation. But what do you notice about this picture? What you notice is that I've taken my partition and I've evaluated my function at the left endpoint of each subinterval over here. That's why we call this a left endpoint approximation. All right. If you take a look at the picture below, in the picture below, I have the same curve. That curve is still y equal to f of x. But this time, I've taken my partition and I've evaluated the height of each rectangle at the right endpoint. So that would be a right endpoint approximation. So we can write down what the areas of these rectangles are going to be, right? So why don't we take a second to do that? So we know that the area is approximately equal to the sum as I goes from 1 to n of the area of the ith rectangle. And I'm really adding those guys up. So when we write out a formula for this, well, what is that going to look like? We're going to call it L sub n. L stands for left endpoint, and n is the number of rectangles we have. And this is going to be equal to, the height is going to be f of x0 times the width, which we set up above was delta x. And then the height of the second rectangle is going to be f of x1, and the width is going to be times delta x. And we keep adding all those rectangles. The last rectangle, the height is going to be f of xn minus 1 times delta x. Okay, and this left endpoint approximation is the approximation for the area. So I want to draw special attention to the fact that we're starting at x0 because we're starting at the left endpoint, and we're ending with xn minus 1 because, again, we're taking the left endpoint of the last subinterval over there. Let's contrast that with the right endpoint approximation. The right endpoint approximation looks like this. Instead of starting with f of x0, we're going to start with f of x1 and multiply by the width of the subinterval. And then the second rectangle is the height's going to be given by f of x2 times the width of the subinterval. And then the very last rectangle, the height's going to be f of xn times, and the width is going to still be delta x. Okay, so when you look at this drawing over here, I could label this guy here as x1, and this guy here is x1, like that. And I just want to point out that x1 is where we find the height of the first rectangle for the right endpoint approximation, and that's the height of the second rectangle for the left endpoint approximation. All right. I also want to emphasize the fact that for the very last rectangle on the right endpoint, we're not doing it at xn minus 1, we're doing it at xn. Okay, cool. So now that we've seen this left endpoint approximation and this right endpoint approximation, I'm in a position to define what we mean by a Riemann sum. So we're going to do example 6 together in class, but let's scroll down here and talk about what we mean by a Riemann sum. So if we let f of x be defined on a closed interval, and let P be a regular partition of this interval AB, Delta x is going to be the width of each subinterval. And for each I, we're going to let xi star be any point inside of here. So we are not specifying the left endpoint or the right endpoint. Okay, we're just going to say, I'm not going to tell you which one it is, it's something in there. And when we define our Riemann sum is going to be the following approximation. It is going to be the summation as I goes from 1 to n. The height's going to be given by f of xi star, and the width is going to just be delta x. Okay, so just as a quick reminder, delta x, because we have a regular partition, that's going to be b minus a divided by n, like so. And just to make it perfectly clear, this f of xi star, that's the height of the ith rectangle. And delta x, that's the width of the ith subinterval. And now you can see why we learned this sigma notation, because this allows us to add up all of the rectangles to get our approximation. Okay, so this approximation right here, this is what we call a Riemann sum. So I hope it's not excessive, but I'm just going to highlight this. This is the Riemann sum right here. All right, everybody, we'll work through some examples in class together. Take care.